So we did a couple of these examples here on what we call the central limit theorem and sampling distributions. So make sure you can do problems like this. You'll see them on next week's quiz. Okay. And so just to kind of summarize, whoops. Okay. So to kind of So the idea is we can approximate the sampling distribution of p hat with the normal distribution. Okay. And again, this is an approximation. The actual distribution of p hat is a little bit more complicated, but to make our lives easier, we're going to say, it's approximately, and we say normal with mean p and standard deviation p times 1 minus p over n. So this is the mean, and this is the standard deviation. Okay. Now, when it's the standard deviation of a sampling distribution, it gets a special name. Okay. The standard deviation is called the standard error. Yeah, question?
Can we go back to the first part? What exactly am I seeing over here? P hat.
So this means p hat comes from the normal distribution. So this is just another way of saying p hat comes from the normal distribution. Okay?
And then the premises for the
And this means has a mean of p, and this is the standard deviation.
Okay, I just for a second thought this I'm seeing a formula over here. That's all.
Yeah, no, I'm just recapping what we've covered already. Okay? Now, the central limit theorem, there was this little clause in there that said if certain conditions are met. Okay? And so I'm going to talk about those conditions. Right? And so the truth is that we can approximate p hat with the normal distribution if these conditions are met. And if the conditions are not met, then the sampling distribution is different from the normal distribution, and the normal distribution does not make a good approximation. Okay? So there are 3 conditions that need to be met if we want to use the normal distribution as an approximation of the sampling distribution. Okay, so these 3 conditions are the random and independent condition, meaning that the sample must be selected randomly from the population. Okay, and members of the sample must be independent of each other. Okay, so if the problem says it was randomly selected, then you can assume this condition is met. Okay, we have the large sample condition. And for this condition to be met, the sample must be large enough. Okay, and what that means is that you must observe at least 10 successes and 10 failures. And at least 10 failures. Okay, and if the success and failure count is not given, okay, if the counts are not given, then n times p and n times 1 minus p must both be bigger than 10. Greater than or equal to 10. Question?
Yeah. What do you mean when you say successes?
So, we're dealing with proportions, right? So it's, what proportion of people are left-handed? When you take your sample of people, you need to have at least 10 people who are left-handed and at least 10 people who are not left-handed. Okay, if your sample is not big enough, if you only get 8 people who are left-handed, then your sample's not big enough. You need at least 10. You need at least 10 yeses and 10 nos, whatever question it is that you're asking. Okay, again, success and failure, these are arbitrary labels, but that's just kind of the label we use.
So for example, 100 failures and 8 successes is not good.
Yeah, 100 failures and 8 successes is not a big enough sample. Okay.
But if it's 110, then it's good.
If you have 100 yeses and 10 nos, then your sample is big enough. Yeah. So you need to have at least 10 and 10. Okay, and then lastly, the big population condition. Okay, and so here, the population must be big compared to the sample. So the population must be ten times bigger than the sample, or more. So it must be at least, I should write, it must be at least 10 times bigger than the sample. Okay, or conversely, do not sample over 10% of the population. Sample over 1/10. Okay. Question, yes.
Going back to the second condition.
Second condition.
The last part, if the counts are not given, then what am I saying with that?
Yeah, so so sometimes in the problem it might say, you know, you surveyed 200 people and you got 50 yeses and 150 nos, okay? It could also say you surveyed 200 people and you got 25% yes, okay? So they didn't give you counts there, but you got 25% yes. So then you're gonna have to do some math and you go 25%, so P times 200, N, that gives me 50, okay? So N times P is 50, that means I got 50 yeses. And if I got 25% yeses, that means I got 75% nos, 1 minus P. And I do N times 1 minus P, and then I would say, oh, that means I got 150 nos. Both of those numbers are bigger than 10, okay? So if you're not given the counts, you might have to do a little bit of math to figure out what the counts are. Okay, and then, yeah, condition 3, big population. The population has to be 10 times bigger than your sample, or conversely, don't sample more than 1/10 of your population. Okay, let's, so you'll have a couple questions on the quiz related to this. So let me try giving you an example, and I'll just say, read through this situation. Tell me if we can use the central limit theorem, meaning we can use the normal approximation, or are certain conditions violated. Okay, so let's say you decide to survey some students at an elementary school. Okay. The school has 650 students enrolled. You randomly select 50 students, okay, for your sample. And you find that 84% of the students participate in some form of extracurricular activity. Okay. Can we use the central limit theorem in this scenario? If not, what condition is violated? Okay, so go ahead and work through this, okay? And don't shout out your answer. Go ahead and I'll give you guys a minute or two to figure this out. Go through the conditions, see if any of them have been violated. All right, let's take a look. Okay, so can we use the central limit theorem in this scenario? What do you think? Yes or no?
No.
And the answer here is no. Okay. And it says, if not, which condition is violated? So let's go through each of the conditions. We have the random and independent condition. Okay. So when we look at the random and independent condition, we see that we've randomly selected 50 students. Okay. So our sample is random. This condition is met. Okay, condition met. Okay. I'm going to go a little bit out of order. We'll look at the big population condition. What is our population? It would be all of the elementary school students, okay? So the population is all elementary school students, or all of the students at the school. And we have 650 of them. And our sample has 50 students, okay? So, yeah, so the population is over 10 times bigger, is greater than 10 times our sample. Okay, so condition met. Okay, let's take a look at the large sample condition. Okay, so here it says 84% of the students participate in some extracurricular activity. So here our P is 0.84. This is technically a P hat. And we have N is equal to 50, okay? So we got to check N times P, or in this case, N times P hat, okay? So we have 50 times 0.84, and we get 42. And we do N times 1 minus P, or 1 minus P hat in this case, 50 times 1 minus 0.84. And when we do that, we get 8, okay? So this one is bigger than 10, bigger than or equal to 10, that's good. But this one is not bigger than or equal to 10, okay? So this condition is not met. Okay, and so in this scenario, we cannot use the normal approximation, okay? Because the rule about using the normal approximation, that only works if these conditions are met. Yeah?
So in the real world, we'll need to draw more people, more sample?
Yeah, you would either have to take a larger sample or something, you know. In this case, because the population is fairly small, you run the risk of taking too big of a sample, and so it cuts both ways. So in some situations you can't use the normal approximation. You have to go into the more complicated math. Okay, but we're not covering it in this class. Okay, is that all right? So on the quiz, you'll have a few questions where you're going to have to read through this thing, and you're going to have to decide if any of the conditions have been violated or not. Okay.
On the quiz, like the first question you go, right?
On the practice quiz, you know, I don't have that pulled up. Maybe at the end of the class, I'll take a look. Okay. All good? All right. So let's do our first bit of inference here. Okay, and we're going to take a look at confidence intervals. Okay, so the idea behind a confidence interval, all right? So let's say I have a new tank here, okay? And in this tank, I've got M&Ms, all right? Lots of M&Ms, okay? And this time I haven't counted them out. Okay, and I want to know what proportion of the candies what proportion of the candies in the tank, what proportion are red? Okay, and right now we don't know. Okay, so but there's too many. There's like thousands of pounds, and I don't want to count them all. So I take a random sample. So I take a random sample of 200 pieces of candy. Okay, I count them up. And 36 pieces are red. Okay, so that means, so my p hat, my sample proportion is 36 divided by 200. 0.18 of the sample is red. So my p hat is 0.18. Okay. Based on this, what can I say about the proportion that exists in the tank, the p? Okay. So based on my p hat, what can I say about p?
One attempt, isn't that too big? Looking to take the 110.
So I just took 200. So, you know, it's a random sample. So again, I got thousands of pounds of candy here, okay? It's all mixed up. Maybe not thousands of pounds, but just lots of candy here, okay? I take a sample of 200 pieces, I dump them out, I count out how many are red. 36 pieces are red. So 18% of my sample is red, okay? What does this say about the big tank in general, okay? Can we say anything? Is the tank necessarily 18% red?
No, one sample?
No, okay. Could the tank be 20% red? Could the tank be 15% red? Could the tank be 90% red?
No. That's very...
Yeah, we would be really surprised if the tank were 90% red, okay? So something in us tells us that, okay, well, you know, the tank is something around 18% red, okay? Maybe 15% red, maybe 20% red, maybe even as high as 24% red. I don't know, okay? And so we're not going to be able to say that the tank is a specific value, but we might be able to come up with a range of values that are plausible, okay? We can say this range of values are plausible. This interval of values are plausible values for the percentage that's red, okay? And if we're getting 18% in my sample being red, then I would assume that the tank is somewhere between, I don't know, I'm just making up numbers at this point, but maybe between 12% and 24% red or something like that. I'm just making stuff up, okay? And we would say, you know, if 18% of my sample is red, then it's pretty unlikely, or I would be really surprised if the tank turned out to be 50% red, or if the tank turned out to be 90% red, or something like that. Okay, so we can come up with a range or an interval of values that are plausible values of p. Okay, so we may not be able to say that the population has a particular value of p. Okay, or actually we won't be able to. Okay, so I'll just say we will not be able to. But we can create an interval of plausible values. Plausible values of p. Okay. All right. So to kind of get at where we're headed, put this thought on hold, and I'm gonna try to make an analog for this that you may or may not like. Okay. We'll see. Okay. So imagine you see a picture, all right? Someone shares this picture, all right? And well, we'll say this is the 30-yard line, okay, on a football field. And I'm drawing a beautiful picture of,
Cow.
it's a dog, okay? Okay, so we have a dog on the 30-yard line, okay? But then we ask, where is the owner? Okay, and we're going to say the owner is invisible. And the dog is on an invisible elastic leash. All right, what are you talking about? Okay, so it's not just a picture of the dog, but the dog's going for a walk with his invisible owner, and the owner has an invisible leash, and it's also elastic. Okay, so, well, right now this sounds rather strange, but we can say, you know, we know some things about the behavior of the dog. Okay, mainly that, you know, the dog doesn't like to pull hard against the leash, okay? So 68% of the time, the dog will be within 1 yard of the owner. Okay? And 95% of the time, the dog is within 2 yards of the owner. So someone knows where I'm going with this, okay? And 99.7% of the time, the dog is what?
3.
The dog is within 3 yards of the owner, okay? Now, technically, because the leash is elastic, and we'll say it's a high-quality elastic, the dog can stretch more than 3 yards away from the owner, okay? But he doesn't do that very often, okay? But he could. If he wanted to be 4 yards away from the owner, he could go 4 yards away from the owner. It's just, he generally doesn't do that, huh?
Is it going to get past?
No, just, this is a made-up scenario here.
You don't know about the owner's behaviors.
Well, yeah, we don't know the location of the owner. That's true, okay? The owner's invisible. So, well, based on this, what can we say about the location of the owner? We see the dog at the 30-yard line. Can we say anything about the location of the owner? Okay, we're not going to be able to say, oh, well, I know that the owner's at the 31-yard line. We can't say that, okay? But we can say something like, I'm 95% confident that the owner's between the 28 and 32. Can we say that?
Yes.
Yeah, okay. So because we understand the behavior of the dog, when we see the dog at the 30, or I'll just say when we see the dog at 30, okay, we can be 95% confident that the owner is between 28 and 32. Is that all right? Yeah.
So I'm trying to imagine that instead of yards, it's a different one.
Okay, yeah, so we'll get there. Don't worry.
It's a z-score, right?
So we'll get there, okay? So, but I just want to make sure we're okay with this saying something like this. We can be 95% confident that the owner is between 28 and 32, okay? And if I want to be more confident, someone says, oh, you're only 95% confident, I want you to be more confident about your answer. Like I'm going to throw a net to try to capture this invisible owner, okay? Then we can be 99, we can have a greater level of confidence, but we just have to cast a bigger net, right? We would have to go from 27 to 33. But when we do that, we'll be 99% confident or 99.7% confident, okay? We can't be 100% confident because technically it is possible. Is it possible that the owner is down at the 26? Yes, it is possible, but that means this picture was just happened to be taken at one of those very rare instances where the dog was very far away from the owner, which is possible but doesn't happen very often. Okay, so the owner could be yeah, the owner could be very far, like could be at 26, okay, you know, or some other place far from the dog. Okay, but we would be surprised because that means this picture was taken at a rare time when the dog went far from the owner. Okay, so the analog here is that the location of the dog is like p hat. Okay, when we took that sample of M&Ms out of the tank, we can figure out the sample proportion. We can see where p hat is. Okay, whereas where the owner is, okay, so location of dog, that's like p hat. Okay, location of the owner, that's p. That's the proportion in the tank. We don't know what percentage of the candies in the tank are blue. Okay, we don't know that proportion. Okay, what we do know though is that p hat follows the normal distribution. Okay, so this is, you know, behavior of p hat follows the normal distribution. Okay. And so because we know that p hat follows the normal distribution, when we see p hat at a certain location, we can be confident that p is close by. Right? Because we know p hat doesn't go far away from p. When we see p hat at a certain location, we can be confident that p is close by. All right, so you guys have this written down? I'm going to flip the slide. Okay. So central limit theorem gives us an understanding of the behavior of p hat. Okay? So in that p hat follows the normal distribution centered at the mean p. Okay. With a standard deviation equal to the square root of p times 1 minus p over n. Okay? So when we take a sample that has a proportion p hat, we can be confident that the population proportion p is nearby. Okay? So in fact, we can say I am 95% confident that P is within 2 standard deviations of P hat. Okay? Is that all right? And technically, it's to be more accurate, rather than 2, we will use the value 1.96. 1.96 is a little bit more accurate than 2. Okay, so we can say I'm 95% confident that P is within 1.96 standard deviations of P hat. Yes?
So 2 changes to 1.96, what happens to the 1 and the 3 z-scores?
We're not going to worry about those.
Oh, okay.
We're going to work with this 95% confidence, and then we'll talk about other levels of confidence. Okay? So we'll just say, you know, for 95% confident, we're going to use the value 1.96. Okay? So in other words, so if you think about the dog, you know, we said the dog was at the 30, and, you know, we're going to go, you know, 2 yards up and down. Basically, we can say I am 95% confident that P is between, and on the low end, what would I do? I would use P hat, and I would subtract 1.96 times the standard deviation. What's the standard deviation of the sampling distribution called? The standard error. Okay, so I'm going to do minus 1.96 times the standard error. And on the high end, I'll have P hat plus 1.96 times the standard error. Is that all right? And,
Where's the owner?
huh?
So where's the owner?
Where's the owner? Yeah, so that's where P is, okay? So we're 95% confident that P is between P hat minus 1.96 standard errors and P hat plus 1.96 standard errors, okay? And because I'm pretty much writing the same thing twice, we'll just say, you know, I am 95% confident that P is within, we're going to write P hat plus minus 1.96 times the standard error. Okay, so I'm basically just taking the plus and the minus and then putting them together, so I don't have to write P hat minus 1.96 standard errors and P hat plus 1.96 standard errors. We're just putting them together. Okay. So far, so good? All right. There is one problem, though, okay? So recall that the standard error is the square root of p times 1 minus p divided by n, okay? If we do this, this standard error uses p, which we don't know, right? The standard error uses p, and we do not know p. Okay, so what do we do? All right, well, we plug in our best value, our best guess for what p is, okay? So we will, we do the best we can. That's what we have to do in all of life. And we're going to plug in p hat as our best guess for p. Okay. And some mathematicians, they went through and they said, well, are there any negative consequences of plugging in p hat for p? And it turns out, no, it's okay to do this, all right? And later on in chapter 9, we'll plug in, huh?
Later on they change their mind?
Well, in chapter 9, we have a different situation, and plugging in our best guess does have a side effect, and we have to compensate for that later, okay? And so this is all, kind of proven at this higher math level than what we're going to cover in this course. So it's just, doing this is not a problem, okay? And mathematically, this is okay. Right? It's like, can you substitute margarine for butter? In certain cases, yeah, no problem. Okay. In other cases, maybe things will go different, right? Can you, like, they replaced the mac and cheese sauce with all natural ingredients, and it seems to taste okay still. So that was Kraft macaroni and cheese. It's now all natural, whatever that means. But it's like,
What was it before?
it was not all natural. Yeah, emulsified cheese. Well, I guess it still is, but and they only told the fact that they changed it after the fact because they know people are like, oh, I want the original. I can taste the difference, but in reality, people can't really taste the difference. So, okay. Anyway, all right. So what we're going to do is we're going to have standard error is equal to p hat times 1 minus p hat divided by n. Okay, and this is we use this for confidence intervals only. Okay, so to sum up, our 95% confidence interval for p based on p hat is p hat plus or minus 1.96 times the square root of p hat times 1 minus p hat over n. All right, hang in there. Okay, so let's go back, revisit our M&M problem. Okay, so we'll go back to the M&M problem. Okay, So in the tank, P is unknown. P being the proportion of red M&Ms. Okay, we take a sample, 200 random pieces of candy. And what we find is that 36 are red. So we have P hat equal to 0.18, okay? So based on our sample, what can we say about P? Okay, well, we're going to create our 95% confidence interval. Which is P hat plus or minus 1.96 times the square root of P hat times 1 minus P hat over N. Okay, so I've got 0.18 plus or minus 1.96 times the square root of 0.18 times 1 minus 0.18 divided by 200. Okay, so this becomes 0.18 plus or minus, and then I'm going to punch all of this out. Okay, so I'm going to get square root 0.18 times 1 minus 0.18 divided by 200, 0.027166. So I'm going to have 0.18 plus or minus. So I'm going to multiply that times 1.96. I'm going to get 0.053. Okay, so on the low end, I do 0.18 minus 0.053, and that gives me 0.127. And on the high end, I get 0.18 plus 0.053, and that gives me 0.233. All right. So my interval, my 95% confidence interval, is 0.127 to 0.233. And I would say I am 95% confident so don't leave. I'm going to take attendance at the end of class today. All right. I'm 95% confident that the proportion of red M&Ms is between 0.127 and 0.233. Yes, question?
Could you go back to the previous page, please?
Yes. Let me make sure everyone gets this down, and I'll flip back. So we're just writing the sentence. I am 95% confident that the proportion of red M&Ms is between 0.127 and 0.233. Okay, if I flip back to the previous page, it shows all of the math or the computations that we've done to get there. Yes, question.
Will you ever have us do a 97%?
Okay, so I'll talk about different levels of confidence, okay?
Are you gonna talk about margin of error too?
Yes, yes. Okay, is this okay?
Thank you.
All right. All right, so let's take a look. So our confidence interval, okay, if we think back to, if we want to be more confident about finding the location of the owner or whatever, if we want to be more confident in our answer, we had to create a wider interval, right? That interval, it's actually just controlled by this value of 1.96, okay? So, we can have different levels of confidence. By changing the critical value. Okay, and so our confidence interval can actually be written as p hat plus or minus, and I'm going to put in this thing called z star times our standard error. Okay, and so z star is our critical value. Okay, and they're just kind of these set values. Okay, and so for 95% confidence, z star is equal to 1.96. Okay, if you want to be more confident, for 99%, 99% confidence, z star is equal to 2.58. Okay, it's just an arbitrary number. All right. Well, they come from the normal table. If you look up 0.995, all right, meaning you'll have 99% in the middle because you got half a percentage on either tail. You got z star equal to 2.58 for. So that creates a wider interval, right? If you're willing to be less confident, for 90%, z star is 1.645. And for 80% confidence, z star is 1.28. Okay, so these are values. Next week for the quiz, you can have a note card. So these are values to write on your note card. Okay, or memorize them, right? Don't come to me next week saying, I didn't write these on my note card. Can you tell me what the number is that I need to use? See? No. Okay. This, the SE is the standard error. When you multiply z star and the standard error together, this is called the margin of error. Okay, so when during the election season they say so and so is polling at this number 47% with a margin of error of 2% or something like that. What that really means is that the interval, their confidence interval, that's what all of these things are, goes from 45 to 49% or something like that. So what we have for the M&Ms is that our sample proportion was 18% with a margin of error of 5.3%. Okay, you add that or subtract that to kind of get the range of plausible values that we have. Yes?
You said these numbers are coming from this table, right?
They're based on the normal distribution, yeah.
Because when I search for 99%, I'm finding a different number.
You get 2.33, yeah.
Yes.
Yeah. Yeah, if you look up 2.58, that corresponds to 0.995, right? And so you don't bother putting this in your notes, but what's going on here is, we're going to have 2.58 over here and negative 2.58 over here. And if you take or if you look up this number, you'll have 0.995, and if you look up this number, you'll have 0.005, and if you take the difference between them, the value in between will be 0.99. That's what's going on, okay? But
I just need to remember what you wrote down over there.
yeah, so don't, I mean, if you're like really into like where all of these things are coming from, yeah, that's fine, but these are really the only values that you need to know. Would I ever ask you to make a 97% confidence interval? No, I would never, I would not ask you, okay? Could someone make a 97% confidence interval? Yes, someone could make a 97% confidence interval or a 98% confidence interval. You would use a different value here, okay? But these are kind of like the standard numbers to use. You know, I don't know, you could go to Starbucks and you could ask for 19 ounces of coffee and they'd probably accommodate that and they'd look at you funny, but you know, the standard sizes are what, 16 ounces, 12 ounces, 16 ounces, 24 ounces, or things like that. You could ask for some, Trenta, which is like a 32 ouncer or something, right? So the Venti, I think, is 24, and but yeah, you could ask for some weird thing size of coffee, but, Yeah, you know, you'd have to go to 7-Eleven for that or something, the big gulp. But, you know, we generally just stick to kind of these designated values, right? 90, 99, 95, these are kind of the nicer values that we stick to. Could you make a 96.5% confidence interval? Yes, you could. Do people do that? Not really. But, you know, theoretically, we could do that, okay? Let me talk a little bit more about this. So let me just copy this statement. So this is the, if you get a confidence interval, here, it says, you know, I'm 95% confident that the proportion of red M&Ms is between 0.127 and 0.233. This is the correct thing to write. This is correct. Okay, let me just write a few things that are wrong. Okay, it would be wrong to say there is a 95% probability that the population proportion is between 0.127 and 0.233. Okay? And the word probability, it is not correct to use the word probability. Okay? Probability only applies to situations where there is uncertainty. Okay? Okay, so let me demonstrate something. Okay, so I've got a coin here, and I can ask you, before I flip the coin, I can say, I'm going to flip the coin, what's the probability that it will land heads? And you would say 0.5, okay? All right, so I flip the coin, okay? And I can ask you the same question. What's the probability that the coin has landed heads? Okay? And at that point, the answer is actually, that was a nonsense question, okay? Once the coin has landed, there's no more probability associated with it, okay? It no longer makes sense to ask what is the probability that it has landed heads. It either landed heads or it didn't land heads, okay? You don't know how it landed, okay? So what you have to say is, I am 50% confident that it landed heads, okay? But it is no longer correct to say that there is a 50% probability that it landed heads, because either it did or it didn't. There's no uncertainty, so it doesn't make sense to talk about probability, Okay.
That's a great example.
Okay, well, I'm glad you liked it. Okay, so here, it is wrong to say that there's a probability that the population proportion is between 0.127 and 0.233. Okay, the population proportion is a fixed value. It's either between these numbers or it's not. We don't know the value of the population proportion, but there's no uncertainty associated with it. Okay, it's a property, like we could, if we wanted to, open up the tank and count exactly what proportion are red. Okay, and there's no uncertainty associated with that number. Okay, we don't know what it is, but there's no uncertainty. So there is no uncertainty associated with the population proportion P. Okay, it is a fixed value, even if it is unknown to us. Okay. It would also be wrong to say something like 95% of future samples will have a proportion between 0.127 and 0.233. Okay, the confidence interval is just about our confidence about the population proportion. Okay. So maybe I should stick in the word population here. It's about the population proportion P. It's not about P hat. It's not about anything else.
Yeah, we should know precisely.
Hmm?
P hat, we should know precisely.
Yeah, P hat you know precisely because it's coming from your sample. Okay, and you have that data exactly. Okay, are there any questions? No. Okay, then we'll end here. And